Good morning, everyone. So you have the GP scripts available on the web page here. So if you don't want to have to type all the commands, you can download that and just copy paste them. So this tutorial will be about functionalities for constructing subfields of a number field and constructing abelian extensions. So these are functionalities that have been around for a long time, but we made a number of changes to them. So we're going to just, see what's new, but also what was there before. So I'm not assuming that you know how to use these functionalities. We'll just review basically all of them from scratch. OK, just one quick thing. If you want to save the comments that you type during the tutorial, you can add a log file. That can be useful if you want to have a look later. OK, does everyone have a working copy of GP and the scripts? Yes? Everyone's ready? OK. So let's start with subfields. So the function that computes the subfields of a number field is NF subfields. So without extra arguments, it will compute all the subfields. So for instance, you input a polynomial, which should be irreducible. And in this example, for instance, we get 6 subfields for our number field. This includes Q and the field itself. Okay. And if you want to restrict to subfields of a given degree, you just give the degree as a second argument. OK? All right, so the subfields are given as pairs. First, you get a defining polynomial for the subfield, and then you get a second element, which, OK, I didn't write them in full here, but the second argument is a root of that polynomial in the big field. So it defines a map that's an embedding of the small field inside the bigger one. OK, so here, just as a check, we construct some element of one of the degree 4 subfields of our field, and we compute its minimal polynomial. And then using subst, we can map that to the bigger field. And well, of course, it has the same minimal polynomial. Yeah.
I'm already lost with the second slide. That's sufficient. Because
yeah,
everything
well.
is y. So the second y.
Yes. OK, so everything is y. Yes. So the. Sorry.
The first thing is just an abstract polynomial, right?
So OK, so this was the polynomial defining the big field, the ambient one, which had degree 8. OK, so everything has the same variable. I guess it's a historical. Sorry.
Historical bug.
Yes, historical bug. So yeah, sorry about that. But yeah, OK. So you have to keep track of which polynomial means what. So this is the degree 8 polynomial that represents the big field. Then you get a vector containing each element of which represents one subfield. OK? Now, for each subfield, you get a pair of polynomials. The first one is a defining polynomial for the subfield. So for instance, here, some degree 4 subfield. And then this second polynomial, so it's going to be a polynomial of degree strictly less than this one. So you should think of this as an element of the big field. So it's like a polynomial in a root of this one. That is a root of that polynomial. So mapping a root of this to that element in there, it gives an embedding of the subfield in the big one. Yes? OK. And so these few lines that I'm writing is just to, well, test that it works as you expect. OK? So the mapping is done by substitution. Maybe just a few seconds to try that. Are there other questions? Of course, feel free to interrupt me at any time. I mean, this is a tutorial, so there's no point if you don't understand what we are doing. Is it working at your computers? Yes? No, not yet? Yeah? Should I go on? Yes? No? Okay, just a small comment. So if for some reason you had initialized an NF structure for your number field, you can just give that as an argument instead of the polynomial. But it's not required, and it can give a small speed improvement, but usually not much. Okay, so so everything I said so far has been around for a long time. Now I just want to mention what's new for those functionalities. So depending on the situation, we will use different algorithms. So if available, we'll use Galois theory with the Galois init function. If that's not available, there is a combinatorial algorithm due to Kluners, which has been in the software for a long time. The problem with that one is that you can have a combinatorial explosion depending on the properties of your field. And so it can be exponential time in the worst case. Very often it's fast, but yeah, it can explode. So what we added is another algorithm, which is based on factorization. And this one is guaranteed to be polynomial time. But for like smallish examples, it will be slower. So we try to make the best, we try to make some reasonable choice between these algorithms. But if for some reason, well, it turns out maybe it's using the combinatorial algorithm, it didn't realize that it was going to explode, then maybe you want to call the other one. So I'm going to explain to you how to do that. So I said it's a factorization-based algorithm. So the factorization that's needed is the factorization of the defining polynomial over the field itself. Okay, so there's going to be at least one root by definition, and then depending on the cases, it can factor more. So that's the factorization that it's compute. That's what takes most of the time in this algorithm. Once you have the factorization, it's fairly fast. Okay. So how do you factor the polynomial over the field itself? Well, you use NF factor, so of the defining polynomial, and then you have to change variable for the polynomial to be able to, because Parry is not going to accept handling a polynomial with the same variable as the elements of the number field itself. So you can compute this factorization, and then you provide a pair as the first arguments, the defining polynomial and this factorization. And that's going to force the function to use the factorization-based algorithm. And also, well, this factorization can be costly. So if you need it for something else, then you just have to compute it once and you give it to the function. It's not going to recompute it.
Are you insinuating that once you have the factorization, the polynomial time algorithm is always fast?
Yeah, I mean, it's OK. It depends on the size of the output. The output can be extremely large because there can be lots of subfields. But it's going to be quasi-linear in the size of the output. So that's the definition of fast. Sorry?
A quick comment. Just the factorization itself is polynomial time, but definitely not quasi-linear.
Yeah, it's. I mean, well, there's an LLL behind it, so. Okay, and yeah, just as a check, we see that. So here we use the different algorithm as the first call for these subfields. So we get different defining polynomials for hopefully the same subfields, and so we just check that with NF is isom. Okay, maybe I give you a few seconds to try these functions as well. So is it clear what's happening here? Why, like this line, for instance, is that clear for everyone? What's happening there?
The second component in the subfields you find happened here to be a very small degree and not a degree 7.
This one?
Yes, and the next one also.
Yes.
They could be in general of degree 7.
Yes. Is there a reason?
Because in the preceding example, it was degree 7.
Just that the example.
Yeah, let me think. It might. So. Yeah, I don't remember how I generated the field. If I did, maybe there's a reason because of the structure of how I generated it. Like, of course, I mean, this is saying that some, like, minus some power of the generating element is in a subfield. So that's, of course, very special. Yeah, it must be because of how I generated the field. I just don't remember the structure. Yeah, usually it will be maximal degree. Yeah, even this one is not degree 7. Yeah. So yeah, I suppose, okay, the fact that it actually finds these small elements is probably due to the structure of this algorithm, which will compute a basis of the vectors of the subfield as a vector space. So it will echelonize it, and so it will. If they're small degree elements, it will probably find them because. Yeah. Okay, ready for the next slides? Yeah. Have you had time to try these? Yeah? Okay. Oh yeah, so, okay. So since there's no canonical ordering for the subfields, we order them by degree, but beyond that, there's no good choice, so they might end up being permuted. So I'm just here checking which of the subfields obtained in the first call and the second call were isomorphic, and you see that this is, I mean, they're not in the same order. Okay.
Yeah, sorry, I think maybe some they were much nicer with the second version, right? Is it?
It's not
more compact and smaller, and
that's not going to always be true. It's a coincidence. You will see some examples where it returns very, very ugly polynomials. So yeah. No, it's not always true, and we could improve that, but we didn't do much in this direction. Okay, so another new functionality. So number fields can have a huge number of subfields. Like in the worst case, you can have, for fields of degree n, you can have n to the log n subfields. So sometimes you don't want to compute all of them, and maybe the degree restriction is not what you want. So we provide computation of only the maximal subfields, so the ones that are not properly contained in another subfield. And so that's the function nf subfields max. It's only based on the factorization algorithm. So here's an example. So we have this degree 16 field, and we ask for its maximal subfields. And here I'm just computing the degrees of those. So we have a maximal subfield of degree 4 and 3 of degree 8. Okay? But you don't have to have the same degree. It can be whatever. Okay? So everyone's clear with what this function does? Just the maximal subfields. So yes, so since it uses a variant of the factorization algorithm, it can take the factorization as an argument. Just a quick reminder here: be careful with priority of variables when you try to factor a polynomial over a number field. So the variable of the priority, the priority of the variable of the polynomial must be lower than the one of the, well, whatever. If it doesn't work, you just do a var higher of the other one.
Var higher is the common to remember.
Right. I mean, yeah. the important function of this slide is var higher. If you mess up priorities, just use a var higher and then try again.
What it does is generate a variable which has the maximal priority higher than anything in existence. So maybe the next step it will not be suitable, but then you can do it again.
What happens if you are var higher, if the t there is not the same? Like
Here and here. So what will happen? So here you can put whatever you want. That will be used just to display the variable when you print a polynomial.
Okay.
And this is just a variable that stores whatever. So I mean, they don't have to be related. It's just that you will.
Yeah, you will just get confused.
Yeah.
If you put that in a loop, all these t will be different variables.
What?
So if you do a loop and do a lot of variar with the same argument, you're each time creating a new variable.
All with
They
the same
happen to
name.
have the same name, because
Okay.
that's what you should have,
Okay.
which is a bad idea,
Okay.
but they're actually different.
Yeah. So
And
it's
put
better
the
to
same.
have just the variable name with
Yeah.
the same.
Yeah, and just once.
It's better to think about it a little first.
Yeah, although, I mean, you could create a polynomial in t with coefficients in t, but not being the same,
It's a very bad idea.
and that
But
it
you
works.
can do
Just don't do it.
Is the error message wrong? It says t is larger than x, but it actually is smaller than x, no?
It depends what's larger or smaller.
I'm not, I don't remember if larger means higher or lower priority.
Because then you
Larger
ask
means
for
lower
higher.
priority.
That is a bit weird.
It's what it was for
Enlargement-
forever, and we
enlargement
didn't.
is low, okay.
Yeah. Yeah, that's why I'm saying, like, don't. If it doesn't work, do a var higher and try again. Don't try to think about the order.
It's a total order.
Sorry, what?
Maybe the warner could give a hint to try and check.
The error message could
Maybe.
point to var higher. Like maybe, I mean,
Trivial to do, but it's.
It's just that I think many users won't be able to fix.
Yeah, but it's extremely confusing because it returns a new variable that can override an existing variable of the same name. So you
Yeah.
are
Just
building
to
the
look at var higher.
and so forth.
so
But it doesn't work in library now.
yeah, and
This is
so
really specific.
maybe the best solution is to use the one I was using in the previous slides, which was to start with polynomials in y, and when you have a polynomial over that, just use x. And this one,
Another option is to use magma. And then you can look and precisely explain what you mean,
Yeah.
which is a good option. It's just different.
Yeah. Okay. Are we done with priorities of variables? I'm not going to mention that again in this talk. Okay, so once you compute maximal subfields, you may want to descend further inside the tree of, the lattice of subfields. So I'm not doing it several times, but here I'm just computing. So some maximal subfields of this degree 12 subfield, and then we get a degree 4 and a degree 6, and okay, we can compute the subfields of the quartic, and it has a quadratic subfield. Maybe one more interesting point of this slide is that you can get pretty ugly polynomials here. Like this is just a degree 2, and you probably have on your computers some very, very big coefficients here. It's often a good idea to use Polyred best to make the polynomial simpler. And so here we see that it's quite a simple quadratic field. Okay, so it's a good function to have in mind. All these subfield functions do not do any attempt at all to simplify the polynomials. Okay.
This is the cost you pay to have a linear time algorithm. If we were to add the Polyred best, then we would get something much smaller, but possibly without controlling the running times. Here,
I mean, not
we
as
have
well.
complete control. Not as well.
Yeah. Yeah, okay, so maybe about these things of descending into the lattice of subfields. So, okay, I'm going to mention just a little bit what happens internally in the algorithm, because there's some part of it that we considered exporting for GPUs, but we didn't so far. So maybe it's good that you know of it, and if it's needed for your application, we may consider exporting it. So the way the algorithm works, it will first compute a set of subfields that are called the principal subfields, and that have the property that you can obtain every subfield by intersecting some of the principal ones. Okay, by taking some finite intersection of the principal ones. So, and there's very few principal subfields, at most n. Okay?
More than maximum ones.
Possibly more than maximal ones, yes.
What is the definition?
Okay, the definition, yeah, I'll tell you later. Well, okay, no, here's one definition. It's the ones that you cannot obtain by an intersection of bigger ones. It doesn't tell you why there's at most n of them, but that's a definition. So yeah, for an example where you have a principal one that's not maximal, if you have a cyclic cyclic octic field, for instance, then the maximal one, there's only one, it's the quartic. But the degree 2 one cannot be obtained by intersecting bigger ones. So it's also a principal one. Okay? So in principle, we could export these principal subfields and the functions that are used to convert between subspaces that are actually subfields and defining polynomials, so that you can actually make the intersections that you're interested in instead of having either everything or just the maximum ones or just a given degree. It might be slightly cumbersome to export, but if you happen to have an application that needs that, we could do it. At the moment, it's not exported. Okay? All right. Okay, so we already mentioned CM field a little bit this morning, so I'm going to still give you a quick reminder. So a number field is called CM if it's a totally imaginary quadratic extension of a totally real field. So in this case, it has an automorphism of order 2 corresponding to this quadratic extension that induces complex conjugation on every embedding of k into c. And so we call that I don't know, the CM involution or the complex conjugation on k. So just definition. And for an application that we had with Pascal, we needed the maximal CM subfield of a number field given as input. So that's what the next function does. So given, so still a defining polynomial for some number field, it will compute the maximal CM subfield if it exists. Of course, some number fields don't contain a CM subfield. So in this case, it will just return the sentinel value 0. But otherwise, it will give you the maximal CM subfield. So remember, the first one was degree 8, I think. And so it contains an imaginary quadratic. The second one was degree 16, I think. And here it contains some quartic CM field. And the way the output of the function is designed, it will give you somehow a certificate that it's a CM field by giving you a model such that x goes to minus x is the CM involution. So in other words, these polynomials will always be even. And if you take out the squares, you'll get the defining polynomial of the totally real subfield of the CM subfield. Okay? So it gives you, so you have the subfield and its CM involution at the same time. Okay, another way to put it is the defining element will always be totally imaginary.
The field itself is CM.
If
is it going to be faster? Or
Then,
no, I mean, you can test if the number field is CM quite easily.
yeah,
Is that going
how, which method would you use for that?
that must be
I mean, basically, this will do basically what you're thinking.
it's not really simple.
I mean, how would you test if a given number field is CM? Either you compute all of its degree 2 subfields and you see if there's a totally real one, or you compute all the order 2 automorphisms. So if you compute the order 2 automorphisms, well, okay, either your field is, okay, if your field is Galois in the first place, you can use Galois and things like that. This will do it. If your number field is not CM, then you will compute the order 2 automorphisms, but for that you will factor the polynomial over itself. That's also what this does. Essentially, it will be the same thing, yeah. Except that this is more general because it will find the maximal CM subfield even if the big one is not CM. In polynomial time, yes. Yeah, that was the kind of the whole point. Otherwise, you could just list all of the subfields and find, well, the biggest one that's CM. Yeah, but this is polynomial time. It only finds one subfield.
What do we say, B maxima? Can't there be several ones?
The compositum of CM fields is CM. So there's if there is a CM subfield, there's a bigger one. There is a biggest one. Yeah, I mean, there's a notion for an algebraic element to be a CM element, and it's the set of CM. The set of CM elements is a field, and well, so an element is CM if it generates a CM field, and you can check that. Yeah, adding and multiplying elements like this is. Yeah, okay. Exercise. Yeah, okay, so just one note. So Paul Redbest will not preserve this property that we have of these polynomials. So if you want to keep track of the CM involution, you'll need to know the change of variable between this reduced polynomial and the previous one. So you can give a second argument to Paul Redbest, and it will give you, in addition to the defining polynomial, the change of variable between the two. Yes?
Maybe you can also do the Paul Redbest for the totally real maximum.
Yes, that's probably a better.
And then do
yes.
the x squared.
Yes.
That's
yeah. But then you have to know which quadratic extension you made, so you can, yeah. Well, okay. We could have a CM Paul Redbest or something, but I don't know if it's important enough. Yeah, so in this case, so I show you, this is the simplified defining polynomial for the CM quartic. And here I don't know if this is a very important function to know about, but you can substitute every x squared in an expression with subst pol. So I'm doing that to get from these expressions that I know are polynomials in x squared, I take out the squares. And so this is a simplified defining polynomial for the totally real subfield of the maximal CM subfield, which is also the maximal totally real subfield of the initial field. Okay. Do you need a little bit of time to try the commands? Who wants a bit more time, or should I go on? No?
You need
Are we good with the maximal CM subfields? Yeah? Okay, so we're going to switch sections. So this first half of the talk was about subfields. Now we're going to talk about, well, overfields on the other side, and in particular, abelian extensions of number fields. So we're going to start with the simplest ones, which are abelian extensions of Q. So all of those are not new functionalities, but it's just a reminder, just so that you know these functions. Okay, so recall that every abelian extension of Q is contained in a cyclotomic field. That's the Kronecker-Weber theorem. And so there's a couple of functions that realize that. So Pol subcyclo of ND will compute every subfield of the nth cyclotomic field of degree D. So, for instance, if you know that there's a single subfield of the degree you want, you can just get it like this. Okay, so here we compute the degree 11 subfield of the 23rd cyclotomic field. But if you want something more precise, like if there's several subfields of a given degree and there's a single one that you're interested in, you will probably want to use Galois subcyclo, which allow you to specify one specific subfield fixed by a given subgroup of Z mod Zn star, which you can specify either by generating elements like this as actual integers mod n. So this is what I do here. So for instance, this giving n and -1 will compute the totally real subfield of the cyclotomic field, fixed by zeta goes to zeta inverse. So yeah, in this case, so there would be, of course, lots of degree 8 subfields, and you just want one of them. And you can also describe the subgroup. Should have truncated here by giving a matrix describing the subgroup in terms of the generators given by Zn star, which computes the structure and generators for Z mod Zn star. Okay, so here I'm just doing one example here of this type, or some matrix defining a degree 3 subfield. And so, yeah, we can check that the discriminant really has the divisors that we expect. Okay, all good with Paul subcyclo and Galois subcyclo. So we're going to do that for more general number fields. So, okay, quick reminder. So in general, the abelian extensions of a number field are the subfields of its Ray class fields. Ray class fields are extensions whose Galois group is canonically isomorphic to the Ray class groups. So of some modulus. So modulus is an ideal plus possibly a bunch of real places of the number field. Trivial modulus is called the Hilbert class field. So maximal abelian unramified extension. Okay. So let's see some examples. Okay, first I want to mention the transcendental methods, which we have not modified, but it's just a reminder that there are these methods available. So for instance, we can do Hilbert and Ray class fields of quadratic fields. There are special methods for those. I guess maybe we could have extensions of CM quartic someday. So yeah, so these are the functions quad Hilbert and quad Ray. And assuming Stark's conjectures, there's also a special function doing it for totally real fields.
There's also Paul class instead of quad Hilbert.
Yes, okay, I forgot this one. Yeah.
I don't know, in this case, example, it's bigger.
Uh-huh. But it's supposed to be smaller. Which does this one use the J invariant or? Okay. In Paul class or in quad Hilbert? In Paul class you can choose the invariant. Okay, so I forgot Paul class in addition to this list.
So quad Hilbert is always small, and Paul class you can choose a large one.
Okay.
Yeah. Quad Hilbert is always better than J.
Okay. Uh-huh. Right. So okay. So I'm not really explaining these comments because we'll review them in the next few slides. Okay. So the one I want to mention a bit further is the Cum of Fury method. So this one. So Cum of Fury is works in every case, but it can be costly because we need to compute the class group and the units of K adjoin pth roots of unity to construct a degree P extension. And then we need to make towers if we have something of higher degree. So there is a function to do that does 1 degree P step, which is called RNF Kummer. You should forget about it now and only use BNR class field, which is a wrapper for RNF Kummer that will do all these extensions and compositums and whatever that you didn't want to think about. And now you don't have to. OK? So let's see how this function works. So, OK, first we'll do some Hilbert class field. So that's the one that's easiest to input. So OK, let's take this quadratic field. So we first compute its class group with BNF in it. So in this case, it's Z mod 3 times Z mod 3. So we're going to have a degree 9 extension. And if you call BNR class field on that, you'll see that it returns a pair of polynomials of degree 3. So it's not going to give you the Hilbert class field as a degree 9 extension. By default, it will express it as the compositum of these 2 degree 3 extensions, which is in general much more compact, especially if you have more than 2 factors like this. OK? So this is the default behavior. It will always try to return it as a compositum of many small extensions. And if you insist on having a degree 9 polynomial, you can do that with NF compositum. So you give it the base number field, the 2 extensions. Here I added these arguments. OK, maybe I could have done without it. It's just this one promises the function that the 2 extensions you give it are linearly disjoint. So it doesn't do some extra work. And yeah. Yeah, to linearly disjoint over this. So it makes it a bit more efficient. And OK, instead of doing the compositum yourself, there's a flag, comma 1, that says, I really want a single defining polynomial. Yeah, be aware that, of course, this can be very large. And if you use the flag equals 2, you'll even get an absolute defining polynomial over Q. Okay, so this one loses the structure of the extension. You don't know where your initial field sits in there, but yeah, for some reason you might want that.
But it's a better polynomial, actually, no? In that case.
This one, then the.
It's randomized.
No, but I mean, it's possible that we do. I don't remember actually what I implemented, but possibly we do an RNF Polaroid best on these 2 guys before taking the compositum with the flag. I'm not sure.
But also, Bernard class field is randomized, and you
also
get every time the same polynomial.
Yeah, OK. You can try it several times this command. You might not get the same polynomial.
You might get a bit smaller, or the next time you run it, or a bit larger.
But I really think I'm doing some Polaroid best somewhere in this function, so that might be the reason. I just don't do the last one because it's always the most expensive one. OK. Other questions?
Do you have an example where the class group is C9?
Do I have one? I have one where there's a C9 somewhere in the middle in the next slide. Yeah. Yeah, because so far we only had to do degree 3 extensions, not towers. But we'll have an example where you won't see that it makes the tower, but you'll see the output. OK. So this was just for Hilbert class field, but in general, you will want a non-trivial modulus and to do array class groups. So let's do an example. So here we'll add a modulus at a prime above 13. And so here the array class group is isomorphic to Z mod 18 times Z mod 3. So here you'll have a piece that is a degree 9 cyclic extension. OK, so just one quick mention. If depending on what you're going to do, you may not want to actually compute the extension. So you should be aware that there's a bunch of things that you can compute without actually computing the extension, and in particular, well, of course, the degree, but that's kind of trivial, but the discriminant from the, well, I can't say the, Andreas, can you say the name of this formula for me? Thank you. Yeah, that allows you to compute the discriminant in advance without computing the extension. It's, of course, simpler than having this degree 108 polynomial and trying to compute its discriminant. I mean, the discriminant of the number field. But if you want the extension, you can do it. So here we call BNR class field of this BNR. And it returns 3 polynomials on degree 2, 3, and 9. So this one defines a cyclic degree 9 extension that was actually internally constructed as a tower of two degree 3 extensions. And OK, so these polynomials will be slightly ugly, probably. And so again, you can simplify them. Now, so remember, we used Polynomial best to simplify absolute polynomials over Q. Here we have the function RNF Polynomial best that simplifies defining polynomials for relative extensions. OK, so we can apply that to these 3 polynomials and get slightly nicer defining polynomials. Well, the quadratic was pretty simple already, but the cubic and degree 9 one not so much. OK. Should I pause a bit? So do you have time to try the functions? Yeah? Is it working? It was the same, but you just give it the BNF. It's the same function.
It's also called BNR.
Yes. It's a single function. I mean, you don't want to add more functions.
It happens to accept the BNF as argument.
Yeah, you don't have to initialize the BNR with trivial modulus. OK, so yeah, again, if we want, we can ask for an absolute defining polynomial, and we can check that the discriminant we computed before was actually correct. But it's a bit tough because it's a degree 108 number field. So there's going to be a kind of ugly discriminant that you will have to factor in principle. And maybe you don't want to do that. So here I'm helping NF disk by telling it, don't bother too much, just factor up to 1,000 and use that, and try to do something with the rest. And yeah, it gets the right discriminant.
But it's not a proof.
Yeah, it's not a proof. Yeah, it's true.
Also, it's better to put 1 million.
It's still not a proof.
Yes. It's closer to a proof.
But it's usually faster with 1 million.
1,000?
Yeah.
Ah, OK.
Oh, God.
OK, so Bill says I shouldn't have put 1,000, but 1 million is better. Anyway. So yeah. I mean, if you want to have fun, you can try without the second argument and see what your computer does. Maybe with some debug mode to see that it's working hard. OK. Questions so far? No, still good. OK, so that was for computing full ray class field. But usually you may want an extension that's actually a subfield of a ray class field. And so you'll have to specify an actual subgroup. So here I'm going to take a slightly bigger modulus. So so I'm going to give it a slightly bigger ideal. And just one note here, you can give the ideal in a factored form if you don't want to. I mean, it's useless to multiply these ideals because the first thing the function will do is factor it. So might as well give it a factorization matrix. if that's how you construct the ideal. Okay, so we get a bigger ray class field here, but we're just going to want a small piece of it, and so we can specify so the extension by giving a matrix describing the subgroup of this abelian group. And so now we call that called BNR class field with this second argument, the matrix describing the subgroup, and it will compute so the abelian extension. So here it's just cyclic of degree 4, so there's a single polynomial, but in general it will still decompose it as a composite term if possible. Okay. And right, yeah, so there's a couple of shortcuts. I mean, well, one shortcut to describe a subgroup. So one common thing that you might want to do is, for instance, the maximal elementary P extension for some P instead of the, I mean, just that gives, yeah, you'll get a basis of all that that by composite terms can give you every possible 3 extension, and so so that's one common use case. So there's this shortcut giving just an integer tells the function of the subgroup should be this. So that can be a useful shortcut. So here, so the class, yeah, the structure was 36, 12, 6, so we get a 333, and if you put a 9, you get a 339 extension. Okay, all clear to here. Yeah.
What about infinite places?
Yeah, okay, just a sec. It's in a couple slides. I give an example with infinite. Yeah, because the field was totally complex here, so not many infinite places to put in. Yeah, so okay, another note. So again, if you can compute the information you need without the explicit field, do it. So so we saw an example with BNR disk. Another well example is so the decomposition of primes. You can use class field theory to know the decomposition of primes without actually computing the extension. So here, for instance, in this big ray class field that had degree, well, 2,500, you can compute the decomposition of primes. For instance, here you prove that this prime ideal of above 313 is actually totally split in this extension, but you wouldn't want to compute this extension. Okay. All right. Okay, so here just one example with real places, as you asked. So I'm doing it over a real quadratic. So you provide the infinite places by giving a list of zeros or ones of length equal to the number of real places. So you put a 1 when you want to pick up the place, and a 0 if you don't want to pick it up. Okay. So you have to provide a pair. This one, so this one here is the ideal, and this has length 2 because there's 2 real embeddings, and I want to pick up these 2 places.
And they correspond to the NF init, the real roots in that order.
Yes, exactly. Yes, they correspond to the roots. To NF dot roots. I guess what's the NF dot roots in that order. Yeah. So in this case, so what we're doing here, trivial ideal and 1, 1. So this means we're looking at the narrow class group, and so this one is just a C2. And so, yes. Sorry. You want to try?
Just 1 second.
Okay. Okay, I'll leave you a bit of time maybe to play around with the functions. Yes. Try to make the functions crash. That would be very useful.
That's too easy.
Okay, or try to make it return the wrong result. That's more fun. Yes?
I wanted to mention that the real places can be specified in two different ways.
Oh, really?
The zero, I mean, just like there is the NFL sign function or NFL embedding. So you have functions that compute things having to do with complex embeddings or real embeddings in the number field, which we don't mention here. So in all those cases, the embeddings are actually in bijection with the complex roots of the defining polynomial. And instead of, and the roots are ordered in some specific way, which are stored in the number field. Instead of a 0-1 list, you can just write the indices of the place you want to include.
Okay.
Except that you have a slight ambiguity, so it needs to be as a vec small.
Ah, okay.
So as a permutation.
So here I could have put vec small of 1,2,
exactly.
And that would be the same.
So instead of if you are having a field with, I don't know, 200 places, you don't have to have 200 zeros. And
yeah, you get vec small 1 and 200, or like, yeah.
So
okay.
It's either include this place or not, 0, 1 vector.
Or vec small of indices.
As a mask for vec extract, basically. So it's two different ways, and it's consistent over all the functions that handle the embeddings.
Okay.
I wasn't sure it was working, but it does work.
Yeah, I would have guessed it wasn't, but apparently it
I
is.
guessed the same, so that's why I tried.
Right. Okay, and so yeah, as before, we can compute the corresponding class field. Yeah, so here I just well, I'll do another example of BNR disk and check that the corresponding extension really is totally complex as we expected, since, well, okay, it could have, with what we computed, it could have had 2 real roots, I guess, but in this case, it actually doesn't have any real roots. And that the discriminant is correct. Okay, and I think that's all I had, so thank you.